So I'm recording this as a follow-on video when talking about Gauss's law applications with cylindrical shells. So I'm just going to scroll up here to say there's another video that talked about the solid cylinders, and if you haven't watched that one, you want to go watch that. But we're going to take a look here at this sort of situation. So I'm just going to grab my definitions here and then take that down here to where I've got cylindrical shells. So the same sort of symmetry applies here. The difference is how we're looking at the charge enclosed. And so the first case that I'm going to talk about is if I have a thin shell, where basically we can think about the charge is all located on a surface which is some distance r from the center of the cylinder. And in that case, what we need to do is we need to think about, again, there's going to be an E field inside that shell and an E field outside of that shell. Can't spell today. Now, if all I have is this thin spherical shell, then inside the shell, the enclosed charge is just equal to 0. Which then immediately gives us that the electric field inside that shell is 0. We could also argue this from symmetry, as we've looked at something else, that, inside that shell I've got charges symmetrically arranged around me, and therefore it must cancel out. Before we looked at it just on that z-axis, the axis of the cylinder, but now we can actually say everywhere inside that cylinder, because there'll be no charge enclosed. So at any radius out from the center until you get to the shell, and then we're going to have the stuff outside of the shell. So outside of the shell, we have to be a little bit more careful. We're still going to have the overall idea that you've got your Q enclosed over your epsilon naught, and then the area of the Gaussian. Where now r is the distance from the axis, and again r is the shell's distance. So since we have a charge enclosed spread out over a surface, that is going to be sigma times the area of the cylinder. But we have to be careful specifying here, because the area of the cylinder is 2 pi capital R L. So this is the area of the Gaussian. This is the area of the charge. So we have a Gaussian cylindrical shell outside of a charged shell. And so putting this together, we're going to see that the electric field is going to be equal to sigma 2 pi capital R over L over epsilon naught 2 pi little r over L, which is going to mostly cancel out. And I'll just mention here again, if we think about limiting cases, I've made one mistake in here. The 2 pi cancels, the little l cancels, but I'm left with big R and little r. If little r is much, much bigger than big R, the E field's dropping off, and at a value of R equals infinity, E is going to be equal to 0, which fits with what we had already talked about as the limits for point charges. When you get an infinite distance away from the charge, you pretty much don't feel any electric field. And then the other case of interest here of R equal to R, and in this case it's going to go to sigma over epsilon naught. So right at the surface, the electric field is directly related to the charge density on that surface. But it drops off as you go further away if you're outside. And then because of sort of the shielding symmetry effect, again, inside the shell, the electric field was 0. So we can find this for a thin shell anywhere. Now, as a slight extension to this, if instead of it being a thin shell, it's a thicker cylindrical, then we have to specify several different radiuses. And just to sort of make this a little bit more clear here, I'm going to have the inner radius of the cylindrical shell, the outer radius of the cylindrical shell, and I'm going to go ahead and give them names. A is going to be the inner radius, and B is going to be equal to the outer radius. And then we have to consider different regions. So again, the E, if you're inside the cylinder, that's going to be where our R is less than A. And that just for language to try and specify this, if my R is greater than B, I'm completely outside of the shell. If my R is less than A, I'm completely inside. And then comes the case of what if my A is sort of in between those two regions. And again, the inside one is the easiest because here we've got no charge enclosed. Here we're going to need to integrate from S equals A to S equals little r. And here we integrate from S equals A to S equals B. And similar to the solid sphere case, we're integrating over a d tau, which is going to have a rho, which could vary with respect to S, an S, ds, d phi, dz. And so our electric field, once we bring everything together, we'll have an integral up on the top, and using our same symmetry arguments, I'm going to have a 2 pi L that comes out, but then I'm going to have to integrate my rho S ds. And then I'm going to have my epsilon naught 2 pi r L. And it's going to simplify down to my integral of my rho S ds. And I'm going to have an epsilon naught r. But that integral up on the top might have boundaries from A to R, or it might have a boundary of A to B. And depending on the function there, you'd go ahead and find that amount. And I'll leave that integration up as a separate exercise for the learner.